Here is a matching type question on general organic chemistry. Study the items in both columns carefully. Try to work out the matching before we solve it together. Let us now begin solving this step by step. We analyze each part to identify the most acidic hydrogen-containing compound consistent with the given answers. Part A. Answer C. The compounds are fluorine derivatives at the sp3 carbon. The acidity of the CH at the sp3 position depends on stabilization of the carbanion. In B, the NMe3+ group is a strong electron-withdrawing group by induction, but in C, PMe3+ is also electron-withdrawing. However, the key distinction, fluorinyl anion, is stabilized by aromaticity in two rings. The PMe3+ group in C is a better leaving group conceptually, but more importantly, C with PMe3+ stabilize the adjacent carbanion through d-orbital overlap, negative hyperconjugation d-orbital participation, more effectively than NMe3+ in B, since phosphorus has accessible d-orbitals. Additionally, D is biphenyl with methyl, electron donating, so its CH is less acidic. Plain fluorine, A, has pKa 23. In C, the phosphonium group increases acidity more than ammonium in B due to p d-orbital stabilization. Hence, C is most acidic. Part B. Answer A. Compound A is 1,4-benzoquinone, cyclohexa 2,5-diene 1,4-dione. Although it appears to have no typical acidic CH like a beta-dictone, among these options we must consider B1, 3-cyclohexanediene has alpha CH between two carbonyls, pK 5-7, C, alpha-keto ester has acidic alpha H, pK 11-13, D, has the carbonate ester. Weight re-examining A shows a 6-membered ring with 2C is equal to O groups and double bonds suggesting a quinone structure. The alpha H in A if it's diamond-like. Actually the answer is A is equal to 1,4-cyclohexanediene or paraquinone. For 1,4-benzoquinone, the alpha H positions are activated by two carbonyls. But comparing A as 1,4-benzoquinone to B1, 3-cyclohexanediene, the alpha CH2 in 1,3-cyclohexanediene is between two carbonyls, pK 5, making it very acidic. However, the given answer is A. Looking more carefully, A may be cyclohex 2N1,4-dione, not benzoquinone, where the CH2 at position 2 or 5 is allylic and alpha to two carbonyls. This would make those protons exceptionally acidic. The allylic activation plus two carbonyl activations makes A most acidic. Part C. Answer B. All are substituted phenols. Electron-withdrawing groups increase phenol acidity. B has para no 2 strong EWG, M and I effects, pK 7.1, D has meta no 2 only I effect, pK 8.3, A has paraethyl, EDG, pK 10.2, C has para NHCH3, EDG, decreases acidity. Paranitrophenol, B, is more acidic than metanitrophenol, D, because resonance donation of negative charge to the number 2 group is possible from para position. Therefore, B is most acidic. Part D. Answer B. Compound A is acetate anion, CH3CU. This is the conjugate base, so asking about its acidity means the H on CH3 adjacent to the anion, not particularly acidic. B. Acetylestone, pentane 2,4-dione, has alpha CH2 between two carbonyls, pK 9. C. Acetone has alpha CH3, pK 20. D. Acetic anhydride has alpha CH3, pKa tilde 25. Acetylestone, B, is most acidic due to stabilization of enolate by two carbonyl groups. Part E. Answer B. Compound A. PHCH2NH3+, benzylammonium, pKa of conjugate acid tilde 9.3. So this is the acid. B. PHCOH, benzoic acid, pKa tilde 4.2. C. PHOH, phenol, pKa tilde 10. D. PHCH2O, benzyl alcohol, pKa tilde 15. Benzoic acid, B, is most acidic with pKa tilde 4.2. Part F. Answer A. Weight. The answer is A is equal to CH3CH2O, ethanol. But propine, C, has pKa tilde 25, ethanol has pKa tilde 16, propene, D, has pKa tilde 43, ethylamine, B, has pKa tilde 35. Actually, ethanol, pKa tilde 16, is more acidic than propine, pKa tilde 25. No lower pKa is equal to more acidic. Ethanol pKa tilde 16, propine pKa tilde 25. So ethanol is more acidic. The answer, A, is equal to ethanol is correct as most acidic. Wait, that seems counterintuitive since terminal alkynes are famous for acidity. But pKa of terminal alkyne tilde 25 and ethanol tilde 16, so ethanol, pKa 16, is more acidic than propine, pKa 25. Yes, A, ethanol is most acidic among these four. Part G. Answer B. Compound A. CH3CO2H, acetic acid, pKa tilde 4.75, B. Plus H3NCH2CO2H, protonated glycine glycinium, the carboxylic acid of zwitterionic glycine, pKa 1 tilde 2.34, C. Anilinium type compound, D. Cyclohexylammonium, pKa tilde 10.6. The alpha-amino group, ammonium, in B, provides additional electron withdrawal making the COO more acidic, pKa tilde 2.34 versus 4.75 for acetic acid. Therefore, B is most acidic. Part H. Answer C. All are nitrophenols. A. Appears to be 2,6-dinitrophenol or similar, B. 4-nitrophenol, C. 2,4-dinitrophenol, D. 3-nitrophenol. 2,4-dinitrophenol has both ortho and para number 2 groups maximizing resonance and inductive stabilization of phenoxide, pKa tilde 4.0. 2,6-dinitrophenol has steric interference making the ring nonplanar, reducing resonance. Thus 2,4-dinitrophenol, C, is most acidic. Part I. Answer B. Compound A. Triphenylmethane, pH3CH, pKa tilde 31, B. Fluorine, sp3CH2 between two aromatic rings forming cyclopentadienylic anion upon deprotonation, pKa tilde 23, C. Dicyclohexylmethane, sp3CH, pKa tilde 50 plus, D. Agmantanylic cage, sp3CH, pKa tilde 50 plus. Fluorine, B, is most acidic because its carbanion is stabilized by the extended aromatic system of two benzene rings fused to the cyclopentadienyl anion, giving aromatic stabilization, 14 pi electrons for the anion. pKa of fluorine tilde 23, much more acidic than triphenylmethane, tilde 31. Therefore, the correct answer is A, C, B, A, C, B, D, B, E, B, F, A, G, B, H, C, I, B. Therefore, the correct matching is A matches C, B matches A, C matches B, D matches B, E matches B, F matches A, G matches B, H matches C, I matches B.